Hi guys, and welcome back to my channel. In this video I'm going to be discussing the Maxwell-Boltzmann distribution, a distribution you probably heard about from AP Chem that describes the probability density function for the velocity distribution of gas particles at a certain temperature, right? You've probably seen this distribution before. It looks something like this. It peaks and then it flattens out. Velocities on the x-axis, some sort of probability densities on the y-axis, and you've seen like that at higher temperatures the peak gets to higher velocities. That makes sense because when you raise the temperature, gas particles start to move faster. So these sort of things you've probably seen in AP Chem. But what I really want to do in this video is show you how we actually derive this and how we can get this from the Boltzmann distribution itself. And we talked about the Boltzmann distribution a while ago, especially when we were talking about discrete energy levels in quantum mechanics, and we had an example with it with the hydrogen atom. But so Boltzmann distribution has to do with basically discrete energy levels. But in this case, the Maxwell-Boltzmann distribution, we're discussing sort of this continuous amounts, continuous like levels of velocity, right? So in this video, I want to show how we can get from Boltzmann to the Maxwell-Boltzmann distribution. Okay, so first I want to remind you what the Boltzmann distribution is, because we talked about it a little bit ago. This is what it looks like. We have the probability of a state, energy state S, is equal to 1 over this partition function, times the degeneracies. The degeneracies is how many states have the same energy, times this sort of exponential term, this exponential decay that decays off with higher energies, which makes sense because higher energies means that we should have less probability, right? So we have this exponential decay term with the energy in the exponent, right? Okay, so this was the Boltzmann distribution, and this distribution tells us the probability of observing a particle in a certain energy state, right? And higher energies have lower probability, and that's exactly what I just mentioned. We have this e to the negative some constant, some positive constant, times our energy. So as the energy goes up, right, we have probability going down. Okay, but this we really stressed at the beginning that this was used for discrete energy levels. But think about it this way, right? Gas molecules, this what we're describing with Maxwell-Boltzmann is gas particles at a certain temperature. Gas particles, right, can have any velocity, right? We can have any velocity. And remember that velocity is related to energy. How is it related to energy? The kinetic energy of a particle is equal to the half mv squared, right? So we have velocity here, and we can have a continuous sort of distribution of velocities. Right? We can have any velocity. It's not like we're only able to go 1 meter per second, 2 meters per second, and 3 meters per second, right? We can have a continuous sort of change in velocity. We can go 1, 1.1, 1.01, we can have any of these numbers. So how can we take this discrete energy level sort of description and make it into a continuous energy level description, right? So basically we need to create a distribution that allows for not just discrete energy levels, but continuous energies. Continuous energies because that means that we can allow for any velocity, right? So we want to extend this distribution to continuous energy levels. Gas molecules can have any velocity and can have, therefore, any value for kinetic energy because kinetic energy is just half mv squared. Okay, so in the next following slides, we're going to describe how we can make this change to extend the distribution to continuous energies. Okay, so this is the first step when we transform Maxwell-Boltzmann to Maxwell-Boltzmann. So remember that we had this term, the energy of each state in the exponent, right? We had e to the negative beta es. What can we plug in for es, right? Right now, we don't know the energies of the states, so we want to figure out some function that we can plug in for, or some equation that we can plug in for es, right? So let's remember something. Remember, kinetic energy is half mv squared, and this is energy. That's the energy of the state. So at a certain velocity, we have that amount of energy, that half mv squared, right? So I can sub in this, equation for energy into my Boltzmann equation. So plugging that in, we have P of V equals, this all stays the same, 1 over z times the degeneracy term times e to the negative beta times half mv squared. So all we've done is subbed in half mv squared for the energy of each state, right? And when we sub that in, we get this 1 over z times the degeneracy term e to the negative mv squared over 2 kbt, right? And the kbt is from the beta, because beta equals 1 over kbt, right? That should look familiar. Okay, so I want you to note a few things. First, remember how we described this as the probability of each state on the last slide, but now we have probability of a velocity, right? Velocity is our input into our probability density function. So what does this mean, right? Velocity, right? The energy state is solely determined by the amount of kinetic energy of the gas particle. The energy state, this is important. So the state is determined by the amount of kinetic energy. The more kinetic energy, the higher the energy state. And the kinetic energy is solely determined by the velocity. So when I have a probability of an energy state, that's essentially the probability at a velocity, because velocity directly gives you the energy state, right? Another question you might have is, we noted that this is like the energy state of that velocity, right? So when I plug this in, when we have e to the negative beta es, we're saying this is the probability my particle is at this energy state. That's essentially what we're saying. But so that should mean that I sum up all the energies, right? My potential and my kinetic energy. Because both of the potential energy, both of those forms of energies is contributing to my total energy of the energy state, right? So if we think about something like that has, say we had 2 joules of kinetic energy, but also we had minus 2 joules of potential energy, whereas another system where we had another state where we had 2 joules of kinetic energy and 0 joules of potential energy, right? So say this was Ke and this was potential. The one with 2 joules and minus 2 joules is going to be favored, right? That's going to have the lower total energy of the energy state, because there's this extra stabilization of the minus 2 joules of potential energy, right? But when we plug this in, we only accounted for kinetic energy. This might be a question you're having, and you might be like, why did we only account for kinetic energy? Obviously, if something has 2 different kinetic energies and different values for potential energy, one of those states might be more stable than the other. But this is where our kinetic molecular theory comes in, right? This is where kinetic molecular theory is really, really important to have a good grasp on. Why? Because remember kinetic molecular theory. What did it say? There's no interactions between gas particles. And what does this actually mean, right? That means, this implies that we don't have to worry about adding potential energy into our energy state equation. Why? Because all gas particles will have the same potential energies. So how does this imply that all of the gas particles have the same potential energy? Another way to think about this is that no particle is going to be at lower potential than another. What does that mean? That means that no one particle is going to be more stable than another, right? Why? Because there's no stabilizing or destabilizing sort of interactions between these particles. So everything is going to be at the same stability or have the same potential energy. So we don't have to worry about adding potential energy, because for all these particles, it's just going to be the same. So that's why we can only worry about kinetic energy and only plug in the kinetic energy equation into my Boltzmann probability distribution. Now let's go to the next slide and modify our equation some more to make it closer to the Maxwell-Boltzmann distribution. Okay, so now we want to determine the degeneracy factor. So remember, we had 1 over z, some degeneracy at a certain energy state, times some e to the negative beta es. We determined what es was. Now we need to determine what the degeneracy is, right? So a good way to think about this is for a certain magnitude of velocity. Remember that when we're looking at this, we're describing this as a probability density function at a certain velocity, at a certain speed. The question we want to ask is, at a certain speed, right, how many possible velocity vectors can I have that give me that same speed, right? That's my degeneracy state. How many possible vectors for velocity can I have that end up giving me the same energy state? And remember, energy state is given by half mv squared, where v here is basically the speed, essentially, right? Because it doesn't depend on direction. It's the magnitude of velocity squared, right? So another way to look at kinetic energy is half m times the magnitude of the velocity vector squared, right? Because kinetic energy doesn't change based on the direction of the velocity vector. So at this same kinetic energy, how many velocity vectors can I have that give me that same energy? That's the question we want to ask. So let's see, right? Say we have a certain velocity. Let's look at 1D, and then we'll extend that to 2D and 3D. So first we'll look at one dimension. One dimension, we just have sort of like an x, an x direction. And with a certain velocity, say we want a velocity of like 2 meters per second, we can either go 2 meters per second to the right or 2 meters per second to the left, right? And these two will have the same energy of half m times 2 squared, right? So there's two degeneracies. We can either go to the left or the right, or forwards or backwards, right? So we have two degeneracies. Now let's look at two dimensions. We're going to look at something like the xy plane. XY plane. And now we want to see how many say I'm going 2 meters per second again. But how many possible ways, think of all the directions we can go 2 meters per second that end up with giving me the same energy state. So I can go 2 meters per second to the right. I can go to the left. I can also go, to the side. All these different directions, right? As long as my vector has a magnitude of 2 meters per second. And you might see that these vectors are sort of drawing out a circle. I can go anywhere with these velocity vectors sort of drawing out a circle, as long as that circle has the radius of 2 meters per second, or 2, right? So basically, if I look at all the vectors, right, all the vectors that are going 2 meters per second in a two-dimensional plane, I end up getting a circle. And the circle has radius 2 in this case, right? But in a general case, it will have the radius velocity v, right? It'll have the radius magnitude of v, or I'll just call it v. So essentially, if we look at this, and now if you take the circumference of the circle, we're sort of describing every possible configuration of the velocity such that we get the same energy. So if we take the circumference of the circle, we basically have every degenerate energy state. Okay? Every degenerate energy state. And the circumference of a circle with the radius v is just 2 pi v, right? 2 pi r. So that's what I've written here. All vectors around the circle of radius v gives us 2 pi v degeneracies. Now we just extend this thinking to 3D, and it's hard for me to draw, but basically we end up with a sphere, right? We have a sphere with a bunch of vectors spanning out the sphere with the radius v again, right? And if we look at all vectors around a sphere, we're basically looking at the surface area of the sphere, which is 4 pi r squared, or with radius equal to the velocity, 4 pi v squared. And that's what I've written for the 3D. So all vectors around a sphere of radius v gives a degeneracy of 4 pi v squared. So 4 pi v squared, because we're looking at a 3D world where gas particles can move in all 3 dimensions, this is our degeneracy factor. And now we can plug that into our equation. P of v equals, now we have this 1 over z, our degeneracy factor, 4 pi v squared, and the exponential factor with the energy state that we saw for in the last slide. Now we just need to finish up this Maxwell-Boltzmann distribution by figuring out what this normalization z factor is. Okay, so finally transforming Boltzmann into Maxwell-Boltzmann part 3, right? In this slide, we're just figuring out what the z factor actually is. So we want to solve for the partition function. And how do we do this, right? This was how it's the same way we did it when we were looking at the Boltzmann distribution. We want the total probability to equal 1. That's essentially what the goal is here, right? We just want to normalize this so that the total probability equals 1. This is a continuous distribution rather than a discrete one. So remember how with the discrete one we took a sum of all of the, all of the e to the negative degeneracies, e to the negative beta es, right? We took a sum over all of these and put that on the denominator as z, because that would ensure that when you summed the entire probability density function together, you would get 1, right? But in this case, we want to take an integral because this is a continuous distribution. So we're going to take the integral over all energy levels, and that means over all speeds, because remember, energy is determined by the speed, the velocity, and we're doing this instead of a sum, right? And we're going to set this total integral to 1. So we take this, and what is all the possible speeds? We can go from 0 meters per second to basically infinity meters per second. And obviously this disagrees with relativity a little bit, right? Because a particle cannot exceed the speed of light. But the probability density is so low up at those high speeds that it really doesn't matter, right? We can sort of neglect that effect. So we integrate over all speeds times p of v dv, right? And what exactly is this doing? This is saying that let's take the probability of a little tiny section. So if I draw this probability density curve, it'll make more sense. So when I integrate, I'm saying let's take a tiny dv, a tiny change in my velocity. This is my v, this is my p of v, and I want to take the area under this curve, right? I'm going to take the area, and I'm going to do this for all v from 0 to infinity. So that gives me my total area under the curve, which essentially gives me the total probability, right? And we want this total area or total probability to equal 1. So that's what we're doing with this integral. And then we set 0 to infinity, p of v dv equal to 1. But remember, p of v is just this, what we found in our previous 2 slides. We can plug that in. And actually taking this integral, we are able to solve for z, because this other part is a function that we know. Z is a constant, so we can solve for z because we are setting this equal to 1, right? The math is not super important. You can do this integral if you want to try, but if you aren't super comfortable with integration, it's not important. The more important part is that you see that we're just taking the integral and setting it equal to 1 because we want the total probability over all speeds to be equal to 1. And with this, we can solve for z, the partition factor, and z becomes this term, which is a little bit gross, but when we have, this is the term that is 1 over z, right? 1 over z. So then we get our final Maxwell-Boltzmann distribution equation, which is this guy, right? It's a little bit ugly, but that's our final Maxwell-Boltzmann equation after we did all these substitutions. And we can do one final substitution. Remember, we have m and kb, right? M is the mass of a particle, of a single particle. Kb is Boltzmann constant, right? But say we don't know the mass of a particle is a kind of a annoying thing to work with. We like more like molar masses, right? So what if I multiplied the number of atoms, or Avogadro's number, not the number of atoms, Avogadro's number, on both the top and bottom, right? If I have a term that looks like m over kb, so say I have a term that looks like m over kb, I multiply the top and bottom by Avogadro's number. What do I get? I get the molar mass over Boltzmann constant times Avogadro's number is just the R, our gas constant. So we can see that there's two places I have m over kb. We have it in the exponential term and in the z factor. So I can substitute this in with molar mass over R, and you can see that's what I did in the final equation. So this is our final Maxwell-Boltzmann distribution equation. And that's the sort of graph you might have seen in AP Chem. That's the actual equation that's behind the graph. And just one thing I want you guys to remember is that Maxwell-Boltzmann is a probability density, right? This is important. It's a density distribution, right? What does this mean? This means that we can never find the probability of a certain velocity, right? If I asked you the question like, what's the probability the velocity of the gas particle is 10 meters per second? Say that's a question. What is the probability? The answer is 0. Why? Because there's infinitely many velocities the gas particle could travel at, right? And if there's infinitely many velocities, there's no way I can figure out what the probability is at a single velocity, right? Because velocity is a continuous quantity. But what we can do is we can find the probability of a range of velocities, right? We can find the probability of a range. Say I said, what is the probability of 10 meters per second, but you could have an error of 0.05 meters per second, right? So this essentially is saying, what is the probability the gas particle is between 9.95 meters per second and 10.05 meters per second. Then what do? I take the integral from 9.95 to 10.05 of my Maxwell-Boltzmann distribution, dV, P of V dV, right? And this gives me the probability I'm in that range. So because this is a continuous quantity, because my velocities are continuous, there's no way I can specify, what is the probability of this one velocity? Because there are sort of infinitely many velocities and that wouldn't make any sense. But I can ask, what is the probability of a range? And how do we find that? By taking an integral with the bounds as the bounds of that range. Okay, so these are Maxwell-Boltzmann graphs, and this is what you've probably seen in AP Chem, right? So I just wanted to show what the equations actually look like. So this guy on your y-axis is basically your P of V, and your x-axis is basically velocity, right? Speed. So at the left graph here is same temperature, different molar masses, so heavier gas particles. The right graph is same molar mass, different temperatures, right? So what is something to observe? The peaks of these graphs, right? If I look at the peaks of these graphs, we have, the heavier gases at the same temperature have the peaks at lower velocities, right? That makes sense, right? So peaks at lower V for heavier gases. This makes sense because heavier gases have more kinetic energy with the same velocity, right? So if I had the same T, that really means that kinetic energies are sort of similar, which means that the heavier gases need to travel slower to get that same kinetic energy. because mass plays a factor in the kinetic energy. Remember, Ke is half mv squared. So at a single kinetic energy, at the same temperature, we have a lower velocity because we have a higher mass, right? So that's why this graph should sort of make sense. We have lighter molecules traveling faster at the same kinetic energy. The next graph, we have same molar mass and different temperature, and you can see again the peaks. The peaks are at lower v, lower velocity, for lower temps, right? The lower the temperature, the lower the kinetic energy, and therefore the lower the velocity. That's pretty self-explanatory. Next, let's look at sort of some limit analysis, right? As our probability density, as our velocity, goes to 0 for both of these graphs, we see that P of V also goes to 0, right? So basically, no gas is standing still. No gas particle is standing still, which makes sense, right? Because everything is sort of moving around at some speed. So, and the other thing to notice is that as velocity goes to infinity, we can see that probability density goes to 0 really fast, right? In both the graphs, you can see they're essentially like 0 at 600 meters per second or something like that, right? So as our velocity gets really high, the probability of that velocity goes to 0, and that makes sense because the faster something is moving, we can't go super fast because we only have a finite amount of energy. So the probability of super fast speeds are just going to be basically 0. Okay, I just wanted to show sort of some examples of how this analysis was useful. And now I want to show you how we can derive the root mean squared speed from the Maxwell-Boltzmann distribution itself. What is VRMS? What is root mean squared speed? That is just square root of the average value of V squared. That's the definition of root mean squared speed. That's why it's root. This stands for square root. Mean is average. Squared is the square of the velocity, right? So we have the average value of the square of velocity and then the square root. Okay, so now we can do this, and if we can actually calculate this from the Maxwell-Boltzmann distribution, that would be pretty cool, right? And we can confirm our formulas from AP Chem. So VRMS is square root average value of V squared. How do we find the average value of V squared? Average value of V squared is equal to the integral from 0 to infinity, that means over all velocities, times V squared, or V squared, times P of V dV. Okay, so this is a lot of, math. Let's see what each of these terms actually means, right? What is P of V dV, first of all? P of V dV is essentially the probability of finding the particle at a certain velocity. Technically, it's the probability of finding it in an infinitesimally small range around the velocity. So, remember how I said you can never actually find the probability of a velocity? I'll show you what I mean by an infinitesimally small range. I mean, say we have a velocity here, and this is P of V, and we take a tiny dV, right? This is basically P of V dV, but dV is basically infinitely small, right? And P of V dV gives me the size of this rectangle, or the probability, and the size of this rectangle is the probability the gas particle, probability the particle is in between the speeds v minus dv and v plus dv, right? That's essentially what we're finding with P of V dV. But this is essentially because dv is super small, right? It's infinitesimally small. So this is essentially basically finding the probability at a velocity of v, right? I know it's not entirely accurate, but because dv is so small compared to v, this is basically the probability of just finding it at V, right? With a tiny, tiny error margin. So basically we're saying V squared times the probability we find something at V, essentially. So what are we doing when we're multiplying these two? Multiplying this P of V dV by V squared essentially is weighting the value of V squared by its probability, right? That's essentially what we're doing. We're taking the value of V squared and taking the weight. How much is the probability that we're at that V? And that when we're multiplying these and then summing it over all the velocities, we're sort of weighting each V squared by the probability, by the, how high the probability is that the gas particle is at that velocity. So say we have like 3 meters per second and it has a way higher P of V, that's going to be weighted higher than something like 5 meters per second that has a lower P of V, right? So that's how we can find the average, because the average should be closer to 3 than 5 if 3 has a higher P of V. Okay, so why do we integrate? This integral just sums up this weighting for all the values of V squared, and that essentially finds the average value of V squared. And when we actually carry out this integral with that Maxwell-Boltzmann equation that we saw on the previous slide, we get the simple 3RT over m. Average value of V squared is 3RT over m, and that means VRMS is the square root of this, which is square root 3RT over m. And this should look familiar. It's the formula you know and love from AP Chem. The VRMS of a gas is square root 3RT over m. So that should be really cool and confirm sort of your understanding of Maxwell-Boltzmann, right? This should confirm that, okay, the stuff we did in the previous slides is correct, because we got to the same understanding that we had from a previous class. Okay, that's basically all I wanted to cover for today's video. I hope you learned something. I hope you got, I hope it was informative. Thank you guys so much for watching, and I'll see you in the next one.